Hello and welcome back to the Advanced Malware Analysis course by myself and Vitaly Kremez. So in this chapter we're going to be looking at initial stages, and in this particular part of the chapter we're going to be looking at malware packers, which are by far one of the most common things you will encounter aside from malware itself. Most malware, if not all of it, is packed, and so it's extremely helpful to understand how to unpack it. So without further ado, let's just get into it. So when I'm talking about a malware packer in this case, I'm referring to software that protects other software through obfuscation, compression, virtualization, etc. So there's a load of different names for this. There could be cryptors, all sorts of things. In this case, I'm just describing it all as packers. Anyway, let's have a look at the different types of packers. So to start off with, one type of packer we have is the free packer. So these are normally created as part of a research project or simply out of interest, and they're very commonly used to pack less sophisticated malware. So I'm going to go over some examples of packers that fall under the different categories in the next slide. But these are normally the easiest packers to actually unpack, as most of the time there will be a unpacker out there for it, so UPX for example. So next up you've got the malware packer. So these are custom packers written solely for obfuscating malware and hiding from antivirus. They're either custom to a specific group or they're sold on markets like hack forums. So these aren't too easy to unpack sometimes, but once you've got the hang of them, they'll be pretty simple to unpack the payload. Most packers for malware follow the same routine, allocating memory, decrypting shellcode, decrypting the actual payload. So most of the time when looking at malware like Emotet or TrickBot, unpacking will become fairly trivial, and you'll probably start noticing similarities in packers between the different groups. Like ISFB, you'll probably recognize them using the same packer over and over again. You might unpack that sample so many times that you know exactly how it works, and then you have a look at a sample of Dridex, for example, and you notice, oh wow, they're using the same packer. And from that, you can start building up profiles on these different threat actors and everything, and that's essentially threat intel. But obviously at the moment we're just looking at packers, so let's continue. So finally you've got commercial packers, which are created to protect legitimate software, typically licensed software, and it's occasionally used to protect malware. So it's unlikely to find commercial packers packing malware because you have to actually pay for them, and who wants to pay for software when you can get it for free? However, you can obviously find cracked versions of VM Protect or ASPack or something online, and as a result, some malware may be packed with VM Protect, which is a huge pain and it's extremely difficult to unpack. But situations like those are extremely unlikely. So we're not going to be looking at commercial packers, as there's a lot of gray area around that. So we're going to be focusing pretty much on malware packers throughout this entire chapter. Again, free packers and malware packers are the most commonly found. So now we've got the different categories of packers. Let's have a look at some examples of them. So in the free category, we've got UPX, NPAC, Mu, Polycryptor, Empress, and PE Protector. UPX is probably one of the most popular ones. It's extremely easy to unpack. Just download UPX and then use the command line UPX-D. In the malware packer, we've got a lot of cryptors. You can probably guess which ones are from hack forums and which ones aren't. We've got Warzone Crypto, Yakuza, Attila, Aspire, and then Spartan. Those are all pretty much from hack forums. They're given the name Crypto. They're probably packers, but they just encrypt the payload. So there's loads of different names. In this case, we're calling them packers. And I've thrown in the Emotet, Dridex, ISFB, TrickBot, etc. packer. They use different ones. They're normally not the same every campaign, but sometimes you'll find similarities. I believe there was a post put out a couple of months ago about similarities found between these four groups using the same packer. So those are normally good for threat intel. If you know there's a specific packer that is only being used by Emotet, it's very similar every time you see it, then you see Dridex using it, it could possibly mean the groups are working together. So finally, we've got the commercial packers. We've got VM Protect, Thermida, Obsidian, Armadillo, ASPack, and then PE Lock. VM Protect is probably one of the worst ones to find malware being packed with, as it's a huge pain to unpack because it implements a VM inside the code. So you'll need to figure out how the bytecode is processed and everything. It's just a drag just to get to a sample that may steal passwords or something. I remember there was an APT that actually used VM Protect on some of their samples to hide a rootkit. So in instances like those, it's important to try and figure out what the rootkit does, so you need to unpack it. But again, it's a grey area when it comes to unpacking it, as it's got legitimate software uses and it's not commonly used when it comes to malware packing. So we're just going to focus on the free and the normal malware packers. So again, as I mentioned before, all the packers with names in the malware packer section are all hack forum packers. So now we're going to go on to one of the most commonly asked questions I get, which is how to detect malware that's packed. So we've got 6 main categories here when it comes to detecting packed malware. So first up, we've got signatures. So tools like PEID or Yaroscan can pick up signatures and detect based on rules. These signatures can range from specific hard-coded values to byte patterns. So this can pick up things like it's got UPX in the section names, so this is probably going to be UPX or something like that. Then we have strings, so a lack of strings or an abundance of nonsensical strings in the binary could be an indicator that the program is packed in some way. Next up we have imports. Once again, a lack of imports or an abundance of unusual imports in the binary could be an indicator that the program is also packed. From there we have section names. So packers commonly add extra sections to the binary, such as UPX. These names could be named after the packer or be completely random. So VM-Protect, I believe, names their sections .vmp123, UPX does UPX0123, and so on. Next up we've got entropy. The entropy is determined by the frequency of recurring bytes. The higher the entropy, the lower the amount of recurring bytes. This usually will indicate the data is encrypted, which is another hint that the malware is packed. Finally, we have the raw and virtual sizes. So raw section sizes signify the size of the sections while not running, whereas virtual section sizes are the opposite. Noticeable differences between the two could also indicate that the sample is packed. So I believe UPX has the raw size is 0, but the virtual size is something like 3000 or something, which indicates that okay, something is probably going to be unpacked and then stored in this region of memory. So the malware is most likely going to be packed. So now let's move on. So now we're going to have a look at common packer functionality in the context of common malware. So in this slide, we're going to be looking at how malware is actually packed. So to start off with, we have a malicious executable. This is developed and then passed to a software packer. The packer will then pack the executable and append an unpacking stub to the packed executable. So the unpacking stub is what will basically decrypt and reverse what the packer does. So let's say, for example, the packer software will go ahead and AES encrypt the payload, and it will then obfuscate it using gzip compression. The unpacking stub will then go ahead and gzip decompress the payload and then AES decrypt it using the key passed in obviously from a packer, and then it will be responsible for loading the unpacked payload into memory and then executing it. So now we're going to look at how unpacking works. So again, we've got the unpacking stub here with the malicious executable appended to it. This will then go ahead and allocate a region of memory inside of the process memory. It will then go ahead and copy shellcode inside of it to memory. So this shellcode could be stored as encrypted, or it could just be in plain text. So it will copy this shellcode to the allocated region of memory. It will then jump to that shellcode and execute it. And this shellcode will then allocate another region of memory. And then it will decrypt the executable and then copy it to that region of memory. So now we've got the malicious executable in memory. It can then overwrite the process memory with the malicious executable. It can inject it into another process or whatever it wants to do. It can even execute it in its own process memory. It doesn't need to overwrite anything. But at this point, now we have the plain text executable, so we can go ahead and dump it out, and we have the unpacked payload. And that's pretty much the goal when it comes to unpacking malware. We don't really care much about how it maps into memory or anything. It's about getting to the actual malware and analyzing it as quick as possible. So now we're going to look at some methods of unpacking common packers in the context of common malware. One option we've got is doing it statically. So this is probably one of the most difficult things you can do, as this involves reverse engineering the entire unpacking routine. And so it's definitely very time consuming. If it's a packer that's used constantly and it never changes, maybe there's a point in writing a static unpacker, which will allow you to unpack every single payload. But most of the time you'll find groups like Emotet or Dridex, they'll change up their packer almost every campaign. And so there's no point really writing a static unpacker for it. So then we've got dynamic unpacking. So using a debugger to place breakpoints on common unpacking functions. virtual protect X, virtual alloc X, and then write process memory. And then you've got automated unpacking. So this is by far the easiest, using automated software, either online or local. A tool like unpack.me, which is extremely useful when it comes to unpacking. I pretty much use it all the time. You've got PE-Sieve, you've got sandboxes. Basically, they usually fire and forget. So you upload the file and it will unpack it all and then dump out the unpacked payload. So static and dynamic unpacking are obviously manually done, whereas automatically is done automatically. So we're going to be focusing on dynamic unpacking as it's the most reliable. You don't need to worry about any offsets being wrong or anything being incorrect. And once you've got the hang of doing it dynamically, you can then start doing it automatically, because then you know if something goes wrong, you have an idea of how to figure out what's gone wrong. So what we're going to do now is let's have a look at our first malware sample and see if we can unpack it. So in this part of the chapter, we're going to be unpacking 4 different malware samples. So we're going to start off with Dridex, then we've got Ramnet, Remcos, and then Zloader. And let's get started with unpacking Dridex. So let's go ahead and extract this. Password is infected, and I'll make sure to upload all the samples to Podia so you can download them and follow along. So this is the Dridex sample, so let's just rename that. So now what I'm going to do is we're going to open it up in PE Studio first to get an idea of the executable itself. So we've obviously got the MD5, the SHA-1 and the SHA-256 hashes. We've got the MZ header, the file size. The entropy is quite high, so that usually is a good indication that it is packed, as the higher the entropy, the lower amount of frequently occurring bytes. Then we have the entry point address, we've got the file version and the description. So this is a key crypt program database DLL. Obviously it isn't, it's actually Dridex, but let's keep going. So we've got indicators here, file references strings tagged as blacklist, invalid, language and everything. We've got the DOS header, DOS stub, optional header, size of the code. So here we can see size of the code is 0 bytes, which is another indication that it's packed, as the size of the code should be a lot bigger than 0 bytes. So as we keep going down, size of headers, section alignment, nothing else really interesting in here other than the file checksum, which is zeroed out compared to the actual checksum. We've got the directories. So we have the RData section, the resource, the relocation, and the text section. So what's also interesting is we see here that this has a timestamp of July 17th, 2038. This has a timestamp of April 24th, 2020, which is yesterday at the time of recording this. So that definitely doesn't align with the rest of the executable. So if we go into the sections, we've got text, RData, data, text1. So that normally isn't there when it comes to regular executables. And then we have the relocation and resources. Looking at the libraries, we've got a few different libraries that are imported. So RP-CRT4, ADVAPI, OLE, AUT32, this PDH.dll, which I've never actually seen before inside of malware. Kernel32 obviously, WinINet, which is interesting, Setup API, User32, and then MSVCRT. Then we look at the imports. We've got a few different imports here, including this get scroll position, and we can move over to the exports. We've got this one export which looks like it's pointing to sleep, so I guess if it's called, it's just going to sleep for a specified amount of time. Then the resources, we have binary data in the resources, and then the version. This is quite interesting. It could potentially be shellcode, although it does have this XL header, which is quite interesting. So we might see that being used at some point if we were looking at the packer in depth. Then we've got strings. So we've got a lot of strings here, WinWord, which is quite interesting, potentially trying to masquerade a Word file or something. We've got obviously the imports here, a lot of junk data here, some more strings, and as you can see, there's a lot more obfuscated or encrypted strings than there are actual strings themselves. So that's another good indication that this is packed. So if we go down now, we can see that the format is unknown. The debugger stamp has been set to July 17th again. And we go to the version, it tells us the language is Korean, and we get the original file name. So that's basically an overview of the executable. To me, it looks definitely like it's going to be packed. As we already know, it's Dridex, it will be packed, although in cases where you don't know what malware family it's from, you might be dealing with something that is just obfuscated by default. So what we're going to go ahead and do now is open it up in X32 debug, and let's see if we can unpack it. So jump to user code to begin with, and looking at it already, that doesn't look like anything I've seen in Dridex before, so it most definitely is packed. So what we're going to go ahead and do now is put a breakpoint on virtual allocate, breakpoint on virtual protect, and a breakpoint on create process internal W, just in case it uses other methods of unpacking and then ends up creating another process. I don't think it will, as Dridex doesn't normally do that, but who knows. So let's go ahead and just step over this, see where it goes. Okay, we hit this, we go back, and then it calls return. So now it will call this function here. So rather than step through it manually, let's just simply run the debugger, and we hit the breakpoint on virtual allocate. So now let's hit the execute till return button, and as the return value for virtual allocate is stored in EAX, let's right click this register here and follow and dump. So this is the recently allocated region of memory. So now let's go ahead and run the debugger again. So looking at the previously allocated memory, if we scroll down, we can actually see something has been written into this region, and it seems to be the unpacked executable, as there's no .text1 section. So this could possibly be the unpacked executable we need to dump out. But let's go ahead and wait until we start seeing the original process map it into memory, so we know for sure that it is the unpacked Dridex sample. So we've hit this call to virtual allocate here. Let's go ahead and follow the return value in the dump again, run the debugger again. So here we've got an executable that looks very similar to the one we saw in the previously allocated memory. So the section table looks identical. As we scroll down, I get the feeling it's probably mapped it into this region of memory, and then what it's going to do is it's going to copy these sections out and overwrite itself. So as you can see, the binary here is starting at the offset of 0x1000. If we go to dump 1, which is the first citing of the executable, and we scroll down, you can see that this offset is 0x6b7, but that's mainly due to the empty memory at the start before the executable began. So what we're dealing with here is we have the unmapped executable in memory here and the mapped executable in memory here. So this was quite easy to unpack, as there was no obfuscation or anything. But let's keep going on and see why they're allocating other regions of memory. So let's go ahead and hit the return, follow this in dump, and run once more. So now we hit the call to virtual protect. So now we have another executable here that looks quite different to the previous two that we've seen, as we have this section of data here. So if we look at the executable that was mapped into memory, we can see that there's data here that isn't present inside of this executable. So if we scroll down, we can also see that this is most likely mapped into memory as well. Yep, starts at offset 0x1000. Let's see if the initial bytes are about the same. So it doesn't actually look like the bytes are the same. There seems to be a lot of CC bytes here, so I believe that's int 3. So my guess is this could be a decoy unpacked payload, which is dumped at the same time, or it could be an additional DLL or something. So what we're going to go ahead and do is we're going to actually wait for it to overwrite the original process memory. So when we dump out the unpacked payload, we know it is the actual unpacked payload and not a decoy or something. So let's go ahead and jump to user code here, and we're going to want to scroll down until we see something like a jump to EAX or something. Here's exactly what we're looking for, so let's put a breakpoint on that. Now I see there's a jump here, so let's put a breakpoint on the return just in case it ends up jumping over it. So scrolling back up, we can see a call to EDX here. Let's break on that just in case they have the execution resume from there instead. And that looks about it. So that's a call to virtual protect we've just returned from. So I'm not going to put a breakpoint on that. So let's run, and we hit the call to EDX, which is another call to virtual protect. Let's go ahead and remove that now. And we're going to want to run again, hit the call to virtual protect. Let's take the breakpoint off of that, return to user code, and resume execution again. And now we've hit the jump to EAX. So let's take this jump. And this is actually the entry point of the Dridex loader. So this is the API hashing routine. It pushes the two hashes there, one for the DLL to load and one for the API to load. We have a few pushes here. There's an int 3 there. But anyway, we know that we have the unpacked payload. If we view the strings, we can only really see one string here, but that's mainly because of the amount of obfuscation and string encryption that Dridex uses. But let's go ahead and open up Process Hacker and scroll down. We've got Dridex here. and we want to go to memory. We can see here that it's located in the memory region of 1 followed by 7 zeros. So let's scroll down in this window, and this is the region where the executable is stored. We can actually see here that this is the original process memory. So if we right click this, save to desktop and name it dumped dridex.bin. So now we've dumped that out. Let's go ahead and open it up in PEBear. And if we go ahead and now view the imports, you'll see that none of them have been resolved, and that's because this is still mapped into memory. So we need to go ahead and unmap it. So let's go to the section headers, and we want to change the raw address to match the virtual address and then adjust the raw size based on that. So we've got the raw address being 1000. This is 2200. This is 2800. And this is 2900. So now we can adjust the size. So this should be 2100 because 2200 minus 1000 is equal to 2100. Then we adjust the size for this. So this is 6000 and then this is 1000. Now when it comes to the last section, we can actually see down here there's this empty space which can be filled. So let's go ahead and adjust this size until the relock section completely fills it. So let's put in 6000. Okay, 8000. Put that there. Okay, maybe C. And that looks like we've pretty much filled it. So now if we go ahead and view the imports, you can see that they have all been resolved. So we've got free console, exit process, get computer name, add vectored exception handler, and output debug string, as well as sleep. And then we finally have the get username from advapi32. If we now view the exports, we can see the loader.exe that the dridex loader is commonly known as. And so at this point, we can be confident that we've pretty much got the correct unpacked executable. So now what we want to go ahead and do before we save this out is we want to go to this image base and we want to change it to the offset we dumped it from. So if we now go into this again, it's 1 and 7 zeros. So let's change this. So 1 and then 7 zeros. So now you can go ahead and open it up in IDA and you shouldn't have any issues with memory offsets or anything. So let's go ahead and right click, save the executable as, and we can name this as unmapped dridex.bin. But yeah, that brings an end to the unpacking of the dridex sample. In the next clip, we're going to be unpacking Ramnet. So yeah, let's go ahead and jump over to that now. So now we've unpacked the first sample, let's have a look at a second sample and try and refine our skills when it comes to unpacking. Okay, so now we're going to go ahead and unpack Ramnet. So let's just extract this. Password is infected. And now we can just change the .bin to .exe. So let's follow the same routine and open it up with PE Studio. Again, we have a high entropy, 1.97 megabytes. So that's also a very good indication that there's some kind of packing going on here, making it a larger size than it actually is. So we have the DOS header, the file header, optional header, directories, and the sections. So we've got .text, .rdata, .data, .resource, .relock, and then it seems to be another .text section, this time with a higher entropy than all the rest. So this is potentially the encrypted payload or packed payload, although this resource section also has quite a high entropy as well, so that could also contain some shellcode or something. So let's go ahead and go to resources, and it seems that it's an AutoIT unpacker or AutoIT packer, which is going to be great fun when it comes to unpacking it. So the debugger stamp says Jan 30, 2018. We got the manifest here and the version. So it's most likely going to be packed. Let's go ahead and open it up in x32 debug. Now run to user code and let's view these strings. So not many strings here, but because it's AutoIT as well, it's going to be quite difficult to step through. So hopefully they'll call stuff like virtual allocate and virtual protect. And we're going to want to put a few breakpoints on some process injection functions as well, just in case it injects itself into running processes. So let's go ahead and put a breakpoint on virtual alloc, virtual protect, create process internal W, write process memory, and let's put one on is debugger present. debugger present, just in case it uses one of the common anti-debug techniques. And let's go ahead and run. So immediately it will call create process internal on what seems to be the same sample. Okay, let's go ahead and put a breakpoint on nt-resume thread, just in case it wants to inject unpack code into it or something, and let's run. So we'll call it immediately, it looks like. In that case, we're going to open up another instance of x32 debug and attach to this process here. So this is connected to the BE01, and so we're going to want to attach to this one. So let's go ahead and hopefully we've got the same breakpoints. No, we don't. Okay, so let's put the same breakpoints on. Create process internal, virtual protect, virtual allocate is debugger present, write process memory. So now we hit that and let's run. So we hit a call to virtual protect. Let's run again. Okay, now we hit virtual allocate. So it looks like maybe it passed an argument or something to it. I'm not entirely sure of how they developed this. So let's run this one. Calls is debugger present. Let's change this to a 0 because there is no debugger present. Let's run again. It seems to call it constantly. Hopefully it doesn't call it too many times. Run once more. Okay, now it just seems to run constantly. So let's go ahead and follow this output in the dump, run the debugger. Looks to be some shellcode here. That's a push EBP. So let's go ahead and now follow this return value in the dump. Right click, follow and dump. Run. Nothing interesting seems to have been copied there. Dump 1 is still obfuscated shellcode. We call virtual allocate again. So let's follow this in dump, run the debugger again. And here we have another executable. So this is actually UPX packed, interestingly, which I haven't seen in a long time. So let's go ahead and actually dump this out before it maps into memory. And we can either go about unpacking UPX manually or just automatically doing it. So let's open up Process Hacker. And this is the sample we're interested in. Also, we can see that this calls virtual allocate. I'm not sure what this process is doing here, as it created another process, so it's quite strange, but let's go ahead and unpack this sample anyway. So this is located at the offset 1D followed by 4 zeros. So jumping over to here, 1D and 4 zeros, this looks like it's it. And yep, that's the correct file. So right click this, save it to the desktop, and UPX packed ramnet.bin. Now we can go ahead and move these to the side. We have the UPX packed file here. Let's now open it up in a tool called CFF Explorer. It will give us information, so it's packed with UPX v3. We can now go down to one of their tools, which is the UPX utility, and let's see if we can unpack this. Obviously, because it's packed with UPX, we can. So now if we go to this again, we can see that it's now not UPX packed. So let's go ahead and save it to the original file. So let's open it up in PE Studio, and we can see that there's some resources here and the strings here as well. We've got a lot of strings relating to WinINet and WS2_32. We have write process memory. PE Studio is very good when it comes to what information they give you. So more process injection here, system time discovery. So at this point, it's clear that we have the unpacked sample of Ramnet. So let's rename this to unpacked ramnet.bin. So at this point, I mean, we've unpacked Ramnet, we've got the UPX packed payload, and then we've unpacked that UPX layer and managed to get the follow-up layer, which looks like at the very least the Ramnet loader. So yeah, that brings an end to the Ramnet unpacking stage. In the next part, we're going to look at Remcos, which I believe uses a .NET packer, so that will be quite interesting to unpack and see if we do it differently compared to the AutoIT unpacker. So yeah, let's go ahead and start unpacking Remcos. So now with those two samples unpacked, let's have a look at unpacking a third sample. So now we're going to go ahead and unpack REMCOS, and the packer it uses is actually written in .NET. So we're going to go ahead and take two different approaches here. So we're going to unpack it first using x32 debug, and then we're going to go ahead and unpack it using the nspy. So let's go ahead and extract it. So the password is infected, and it looks like it's another WinRAR archive. So let's extract that again. And here we have the REMCOS binary. So now let's open it up in PE Studio. So we can see it's a .NET binary. We've got the MZ header. Quite high entropy again, interesting description, and we have a lot of resources here as well. Manifest version, so there's only one import, which is the core exe main. So the reason there's only one import is because most of the stuff is in .NET, and I don't believe PE Studio parses the .NET correctly, and so most likely what will happen is the .NET packer will load API dynamically. So the sections, we have .text, .resource, and .reloc. And yeah, that's pretty much it. I mean, we've got a few indicators here, although they seem to be about this apparent URL. I don't think that's the URL, I think that's the version. If we check the manifest, we can see here version is 1.0.0.0. And if we go to this version thing here, it tells us the product version, everything. I think that's what it's picking up as apparent URLs. So let's go ahead and open it up in x32 debug. Now, because it is .NET, it's going to be quite difficult to unpack with x32 debug, as this is mainly based around debugging malware written in C or C++ or any sort of those languages, not .NET. However, it is still possible. So we're going to want to put a breakpoint on a few different API calls. So we're going to want to put a breakpoint on virtual allocate, a breakpoint on virtual protect, a breakpoint on is debugger present, and let's put a breakpoint on create process internal W. So we've got these 4 breakpoints here. What I'm going to do in this instance is when we run it, I'm going to allow it to hit the virtual allocate breakpoint a few times. If I haven't found an executable inside of any of the allocated regions of memory, we can go ahead and take the breakpoint off of virtual allocate and virtual protect, and we'll keep it on create process internal, because a lot of the time it will throw in different instructions, like virtual allocate is being called only to allocate regions of memory for its own unpacking thing. It doesn't actually have the executable in it, and because we're not running in dnspy, it's not easy to understand what's going on. So I also want to change the settings. So we go to options, preferences. I want to turn on the break on DLL entry, and that's because REMCOS is actually developed in C++, I believe. So as REMCOS is written in C++, it means that the .NET packer has a few options, one of them being to load it as a DLL, or to inject it into another process, or to simply invoke it if it's an executable. So while we are going through this, I'm going to open up Process Hacker just in case we see it execute anything like another executable or something that's not gone through create process internal W, which would be quite unlikely, but anyway, let's go ahead and start unpacking it. So let's run the debugger. We hit the entry point. So as we have the break on DLL entry, let's simply just keep running the debugger constantly until we get anything useful. So I'm just gonna keep pressing F9. Okay, we hit virtual protect. Okay, seems to be calling virtual protect on a few things. So now we've hit a breakpoint on user 32 DLL. Okay, it's loading in some more DLLs here. Okay, virtual protect again, another entry point. And here we break on virtual allocate. So let's hit the return. And because it's probably being handled by .NET, it will first check if it can actually allocate a region of memory. And if it can, then it will allocate it rather than allocating on the first attempt. So now if we run again, we hit virtual allocate again, hit the return, and now this has been allocated. Follow that and dump. Now we run again. So we hit virtual allocate again, and this region of memory seems to have been filled in with nothing really useful at all. Just seems to be FF bytes and what is possibly a lookup table here. So let's hit the return here. We can't follow it and dump this time, so let's run it again. Return, can't follow it and dump again. So this is the problem with debugging .NET inside of x32 debug, is a lot of the time you'll have multiple calls to virtual allocate that won't actually do anything. But let's run again. It's not actually written anything into the region, although we've still got the FF bytes up here. So let's follow this one more time. Nope. Hit the return. Okay, still nothing. We've now hit a call to is debugger present, so let's hit the return there. Change this to a 0, run again, hit it again, change it to another 0. Hopefully things are going to start ramping up soon. So now we hit the return. Can we follow it in dump? Yeah, we can. And again, nothing really interesting here. I'm probably going to run this once more, and if we don't find an executable, we'll take the breakpoint off of that. Okay, nothing really interesting there. So let's remove the breakpoint on virtual allocate and let's run. Okay, we hit virtual protect now on the PE header here. I'm not exactly sure what this is, so let's follow this in the memory map. And it's just a legitimate library, so we can ignore that. Okay, virtual protect again. Okay, now we've hit an entry point of OLE. Another entry point. Okay, we've hit is debugger present for a third time. Change that to a 0. Run again. Entry point again. Another entry point. We've hit virtual protect once again. Meanwhile, we're monitoring process hacker just to see if any processes are created or not. So it looks like nothing interesting is happening at the moment. So what we can go ahead and do is, I'd say, remove the breakpoint on virtual protect, because unless it's paired up with virtual allocate, it's not very useful. So now let's run the debugger again. Okay, we've hit what seems to be an exception caused. Run again, another exception. Okay, we hit shell 32 entry point. Another entry point. Looks like it's loading in some WinInet calls. Some WMInet, quite interesting. Keep going, GDI, Windows codecs, and here we've hit a call to create process. So from the looks of it, it's going to be creating the same process, the remcos.exe, and it actually passes in the for flag here, which means it's going to be creating it in a suspended state. In that case, let's put a breakpoint on nt resume thread, just because if it resumes it immediately, we can actually break on it and then attach to the process if needed. So now let's also put a breakpoint on write process memory, just in case it is injecting the unpacked payload into the created process, which is highly likely at this point. So now we go ahead and click run. We hit another entry point here, hit run again, and here our breakpoint on write process memory gets hit. So now if we look through the stack, we can see the handle it's writing it to. I believe that's the address it's writing it to, and the data that is going to be writing. So if we right click, follow dword and dump, you can see we have now got a executable header. So now let's scroll down. We've got different sections, so it's not just injecting the same process. We've got .text, .rdata, .data, .resource, and .reloc. Let's go ahead and scroll down, see if there's anything else here. Okay, so we've now got the executable content. So in that case, let's go back to the MC header, and we want to scroll down all the way to the end of the executable here. And I'd say it's probably close to here. There's no more data, I don't believe. So let's select all of that. Double check there's nothing at the end. Nope. Okay, now right click, binary, save to a file, desktop, remcos dump.bin. So now we have this on the desktop. Let's open it up in PE Bear, because I think it's actually mapped into memory. If we go to the top, we can scroll down and see the offset at which it's at. So this is at 330. So it looks like it's possibly being mapped into memory already. So now if we open it up in PE Bear, view imports. Okay, no, I was wrong about that. So it has everything loaded in, luckily. So we don't need to unmap anything. So in that case, this looks like we have the unpacked remcos binary. Let's just see if there's anything else interesting here. We've got resources, ID 0, ID 1, ID 2. So let's go ahead and open this up in PE Studio. We can see it's Microsoft Visual C++, which is a good thing to see, as that means we've now fully unpacked the .NET stuff. We can see the entropy is extremely low, probably no encrypted strings or anything. Indicators, strings blacklisted, contains another file inside of the overlay apparently. We've got libraries that are blacklisted and import symbols. So if we go to libraries, we can see that this WinMM has been blacklisted. We've got WS2_32, so WinSock is being loaded, URLmon, WinInet, The imports looks very much like a stealer. We have a lot of stealer / keylogger related functions, and then we've got screenshot stuff here. We've got what seems to be recording API here. So now if we go to resources, we can see there are 3 resources in total. This is a settings resource. I'm guessing it's probably the configuration, probably encrypted as well. And now if we go to strings, we can see that this is most definitely unpacked. We've got strings relating to registry keys. This event viewer string and this registry key are commonly used for privilege escalation. So that's most likely what it's being used for. If we scroll down, we've got a load of AV C++ compiler strings here. We've got create object, so probably some scripting stuff, install VBS, uninstall VBS. And here we have what looks to be the logging for remcos, so data start, info, error, uploading file to command and control server, offline keylogger has started. We've got the keys is going to keylog, the paths to Chrome saved data. And here we go, we have the first string that directly links this file to remcos. So we now have successfully unpacked remcos using x32 debug. Let's go ahead and try and unpack it using dnspy. Okay, so now we're going to go ahead and open this up in dnspy and see if we can unpack it through that. So dnspy x86, let's close that out, wait for it to load up. Okay, now let's go ahead and throw remcos into here. So this is the packed version, it's not the unpacked version. Let's open up the functions list here, see what we can find. So the entry point is wpf application1.program.main. Let's go to main. We have some application functions, that's not what we're interested in, but this is the next call inside of the program. So about box1 and then my object. Okay, and then we have for each type in main window.monoflat_b.getTypes. So this is another function in the binary. So it will seemingly loop over everything this function returns and set a flag based on if type.name is equal to main window.this function to string. So if we go here, this string is actually equal to 88 converted from an integer to a character plus x. And 88 is actually x itself. So the string is actually xx. So in that case, if type.name is equal to xx, then it will set the flag to true. And if the flag is set to true, it will pass the type into this function here, array xx. So if we go into here now, we've got the type HL. It will perform a few more things here. So it'll set the flag 2 to true if the length of text2 is more than 2. And flag 3 is set if num2 is equal to 4. And if flag 3 is true, it will call this class1.x and then HL. So it doesn't seem like x is an actual function here. It doesn't seem to take me to the function call. So I'm guessing this is probably dynamically located or something. So let's go back to the previous functions. So where array x was called. Okay, so this is where it's called. So we want to go into this monoflat_b here. So we'll do a few more calculations that we saw in the previous one. We've got the variable result being declared as an assembly variable, and that will contain the data from appdomain.currentdomain.load and then mainwindow.monoflatxb. So this is a .NET call, so it's nothing important for us. It will just load assembly in. So it's going to try and load whatever this function here returns. So this function is actually down here. So this will get a key from the resources. So it'll search for the string XX, and that's the key of whatever it's going to decrypt. And what it's going to decrypt is the resource XX plus XX plus XX. So 6 X's in a row. So it will pass in the resource name with 6 X's as well as the key. So now if we check out this dmonoflat ECXES function, we can see it's a simple AES 256 ECB decryptor. So whatever's stored in the resources is just encrypted using AES. So in that case, let's go ahead and put a breakpoint on this function here, because then we can see what is decrypted. So let's back out of this again, back again. So we want to put a breakpoint on this instruction here so we can see which one is the correct type. So now if we go ahead and actually debug the sample, click OK. It will load everything in. Now we hit the breakpoint on the AES decryptor. We can see the data here. Say yes. Okay, so this is encrypted data. Minimize it. Now we want to step over. So now we're back in the calling function. We have two things here. We've got the create decryptor, which is seemingly just a decryptor that can be used again. And then we have this transform final thing, which is the same size almost as the data in the last call, so in the decryptor. So let's go ahead and view this. And as you can see, we've got a MZ header here, so 4D5A. So now, because what's happening to it is it's going to be loaded in by .NET, as if it is .NET, I'm going to assume it's not the remcos payload and is probably something else. So let's go ahead and return from this function, and we want to step over this again, return the result. Now we step over this, okay, step over again. And we now know there's an executable here. So let's go ahead and put a breakpoint on this instruction. Now let's continue. So we check the flag here, run again, checking the flag. So my computer, my project, my web services, thread safe object provider, and then we've got name X. So if we step over that, we set the flag to true, and then we call this array XX function. So let's step into this. We want to step over these things here because they're not really interesting. We do the flags. Flag 2 is true. And now we get to the class1.x and we pass in HL. HL in this case is the assembly to load. So this XCGKLANE library. And what is class 1 in this case? Is it possible to see? No. Okay. So class 1 seems to be another library loaded in. So here we've got the original remcos payload that's packed. And here we have this other library that's apparently been loaded. So let's just go back into this. Where were we? Okay, so let's jump into class1.x. So this is simply used to invoke instructions. So what we want to do is put a breakpoint here. We want to run the binary. Doesn't seem to do anything. Okay, now we hit this function again. So it seems to call it once more. This time we've got lol and full name lol again. Step over this. Apparently the flag is set. So type.name is equal to that string. I believe it's probably been overwritten or something. So it'll call if flag again, and obviously it's not equal to XX. So let's continue again, see if anything changes. Still checking the flags, and it seems to just have returns. So let's check process hacker, and we can see something has decided to execute while we weren't watching. So now let's go ahead and start this again. Don't break. Now we know where we want to go to. Let's F5 this. And let's remove the breakpoint off there. F5, we want to step into this. So let's step in. And we want to put a breakpoint right here, run to that, and step into this. So now our breakpoint before didn't trigger. So now we're actually executing from this class library thing. And we're most interested in the invoke instruction. So we want to physically enter this and follow it along so we can get to the entry point of the next loaded library or something. So let's step into, but this is get methods, we don't want that. Step out, step in again. So now we're inside of invoke, step inside of invoke again. So let's scroll down. So we've got get executing assembly is safe for reflection, get resource string, demand, perform security check, and then we want the unsafe invoke internal. So put a breakpoint on there, run to it, step in. So now we've got a invoke method with arguments and an invoke method without arguments. So we put a breakpoint on both of them. Now we want to step over. Now let's step into this, and it seems to return immediately. Nothing interesting happens there. That's quite strange. Okay, let's step in again, probably because there were no arguments or something. Now if we step over, it now calls the one with arguments. And in this case, the arguments are an array and a pointer to the file name. So now if we open up this array view, we can see there's an executable here, which is even more interesting as it's obviously been decrypted or something. So let's right click this, and we want to show in memory window 1, right click this, and now save selection to possible remcos dump.bin. So now we have that here. Let's open it up in PE Studio, see if it's C++, and it is. So entropy is a bit higher in this case, but it looks pretty much identical to the dumped file we got last time when we unpacked remcos using x32 debug. We've got some strings here. We have the possible privilege escalation strings. If we scroll down, we've got the keylogger stuff, and we have the remcos string. So that pretty much sums up how we can use dnspy to unpack a .NET Packer. So the most important thing to take note of is how we made sure we were stepping inside of the invoke functions, because with dnspy you can't specifically tell it to break on entry of other things. So the best method to do that is just to step into the invoke functions. And when you get to invoke method, if we actually step into this, it will go to the entry point of the DLL that has been loaded. So this looks like it's probably responsible for executing a process or something. So yeah, that pretty much wraps up the unpacking of REMCOS. And so in the next clip, we're going to go ahead and unpack zloader. So now we've got one final sample to unpack. So let's just jump into it. So now we're going to go ahead and unpack zloader. So let's once again extract it, infected, okay, and rename this to zloader. So this is actually a DLL this time. So let's put it into PE Studio, and quite a low entropy compared to the last few samples, although that just might be the way they decide to encrypt things. So file header, April 2020, optional header, directories, we've got the sections here, so .text, rdata, data, resource, and reloc. We've got the 3 imported libraries, which there's quite a few functions on, so it could very well be unpacked. We've then got the imports here, is debugger present and everything, reg query key, rfile APIs ANSI, output debug string, and a few other functions. We've got a few resources here as well, although one looks to be a manifest, and one seems to be a version, and the others seem to be string tables possibly. So in this case, the strings are a huge indication that it is packed. So we can see strings like this path, there depend, port string these office people Unitrain. That's a very interesting PDB to have. We've then got these AV strings here. So you commonly see strings that look like these inside of packed malware samples. We've got a few API strings here, and then a lot of the strings inside are actually quite encrypted. So what we can go ahead and do is open this up in X32 debug and see if it is actually packed or not. But first, let's check the debug path. As you can see, it's got an issue with that. Manifest, and then we've got the version b.dll, and then we've got term move w seam corporation, and there are also no exports. So what we're going to go ahead and do is let's open this up in X32 debug, run to user code, and let's see what strings are in here. A lot of compiler strings and everything, like floating point support and everything. These are normally good signs that there is some form of packer being used. So let's put a breakpoint on virtual allocate, virtual protect, create process internal w, and is debugger present. So now if we run the debugger and just wait to see what happens. Now if I remember correctly, the wait time for zloader is quite a while when it comes to unpacking it. So now we hit virtual allocate. So let's hit the exit and follow and dump, run again. This looks very much like shellcode. We've got what seems to be a short jump or something here, and very shellcodey at this point. This here, I guess, could be an executable just because of how close it is to the shellcode, although it is quite small. So we hit virtual allocate again. Let's go ahead and hit the return, follow and dump, and run. Okay, nothing useful here. We hit virtual allocate again though, so return, follow and dump, run once more, and here we can actually see that this is a obfuscated executable header. So you can see this program cannot be run in DOS mode, and I guess based on the obfuscation, it could be something like aplib, which is quite common in malware. ISFB likes to use it to hide their config. So we know it's compressed, and we can see it's already starting to map it into memory, which means that they've probably used something like heap allocate in order to allocate memory to contain the decompressed executable, or DLL in this case. So let's hit the return here, and now we need to hit the return again. So what we're looking for is a pointer to a region of memory that may contain our executable. So let's step over, we move this into EAX. So that's pointing to a memory offset inside of zloader. Let's follow this in dump. Okay, and immediately we can find an executable here. We've got the text, rdata, data, resource, and reloc section. So what we can actually go ahead and do is let's follow this inside of the memory map. And as you can see, it actually points directly at our main DLL. So this is just the packed DLL, so nothing really helpful there. Continue down, we move the same address into EDI, and then we move this into ECX. So let's follow this and dump. Okay, let's scroll up. Nothing too interesting here from the looks of it. So now let's keep going down. We move this into ESI. Let's follow in dump here. And this is actually looking quite promising here. We've got the text, rdata, data, and relock section. And then we have the actual payload. So this seems to be the unpacked payload at this point. We've got the compressed one up here, and then we've got the decompressed one here. So rather than dump out this whole region of memory, we can go all the way to the bottom, because there doesn't seem to be anything else here. Like if we scroll up, it's just zeros, which would only mess with the hash of the executable. Let's scroll up as far as possible as we can to the data. Okay, there it is. We want to make it as small as it can be without making it too small and taking off necessary data at the end. And I'm going to select this data here. Now right click, binary, save to a file, desktop, and we want to name this dumped zloader.bin. So because it's not mapped into memory, we don't need to open it up in PE-Bear. Let's open it up in PE Studio instead and see what we can find. So the signature is pure basic DLL apparently. It's a DLL. The entropy is still quite low. Directories seem to be invalid apparently. Sections, we've got the 4 sections here. Libraries, this time we've got a lot more libraries to it. So GDI user 32. The imports, we have quite a few imports in this case. Strings, we have a lot of strings here as well. Possibly junk strings. Scroll down, okay. Nothing too useful here until we get to this here. So when it comes to unpacking samples, if you're unpacking a sample for the first time, it's normally quite difficult to determine if you've unpacked it in some cases. In the case of Zloader, they use immense amounts of obfuscation and string encryption, so it's not the easiest. But I've looked at it quite a lot before, and I believe that this string is what's used to decrypt the configuration. So at this point, I'm thinking that we've most likely got the unpacked payload based off this string alone. If we scroll down a bit more, we can see a few more junk strings, nothing really useful. So I'm guessing at this point, this is most likely the unpacked executable. Let's just go ahead and double check that by actually executing it. So we're going to go ahead and put a breakpoint on this return here. So when we were looking at DryDex, there was actually a jump to EAX. In this case, there's no jump, it's only a return. So if we jump into this function here and we see the return, you'll see that before it calls return, it will pop a few registers off the stack. In the case of this return, nothing is being popped off the stack except for ECX. So what I think is going on here is it's actually using that to return to the unpacked code. So at the top of the stack, theoretically, should be a pointer to the unpacked executable, or it will return back from the shellcode to the unpacked executable. So if we now run this, run again, actually let's remove the breakpoint on virtual protect. Let's run. We hit the XOR instruction, step over that. You can see at the top of the stack here, there's a pointer to our unpacked code. So now if we take the return, we've now hit the unpacked Zloader code. So in this case, it looks like it's pretty much going to exit either way of whatever is stored in ESP+8. So I would guess that's mainly because the way we've executed this. Normally when the Zloader infection begins, is run through run-dll32. Obviously in this case, it's running through DLL loader. If we actually go ahead and open up our dumped Zloader inside of PE-Bear and view the exports, we can see that the main export is DLL register server, and that would normally be executed, but in this case it's decided that it won't execute that because we're not running from the correct process and we're actually running from DLL loader. So if you were to execute this through run-dll32, you'd notice that it actually starts executing the main functions. But yeah, that's pretty much it. We've managed to unpack Zloader properly. This is the hashing routine it uses. So this is probably going to load from kernel 32. This is the hash of the API it wants to load in. And yeah, that pretty much brings an end to unpacking Zloader. We've now unpacked all the samples that I'd selected out for us to unpack. So yeah, that brings an end to this chapter as well. So to recap this part of the chapter, we looked at different types of packers, different methods of detecting whether malware is packed or not, how common packers operate, as well as unpacking 4 different samples. So that pretty much brings an end to this first part of the chapter. So in the next part of the chapter, we're going to be looking at first stage loaders. So these are typically Word documents with malicious macros in it. And once we've had a look at that part of the chapter, we're going to move on to the next part, which is second stage executables. And that's where the unpacking knowledge that we've just learned in this part comes into play, as most of the time second stage loaders will be packed in some form. But yeah, that pretty much wraps up this part of the chapter. So I'll see you in the next part.